Okay, we start up again. I have put out on your homepage now the SOLA code, the algorithm, MATLAB script. And I will just go through a little bit of the details here so you can start playing around with it. The algorithm will be the same as I wrote down for the projection method, time split method. You start by calculating the tentative velocity field based on the old pressure. Then we are solving this Poisson equation for the pressure difference. And then we adjust the pressure during the iteration process. But in the algorithm you will be given, we have also adjusts the velocity in the same at the same time. It's a little tricky. It's quite elegant, very compact, but not so easy actually to see what's going on. The philosophy is a little bit like this. If you have one cell, you calculate the divergence for this entire cell based on these four velocities. If the divergence is positive, that meaning you have a net flux out of this cell, then you decrease the pressure inside, sort of to make the flow go more inwards into the cell, and vice versa. If the divergence is negative, that means you have a net flux in, then you increase the pressure inside the cell to push more fluid out. And that's actually what's been doing here. And also it's been done in a way to ensure that you don't induce vorticity. So we don't have to go into the details here. Just believe me when I say you are solving the equation system, the equation here, with SOR. But we are doing it in a sort of a special way. And then finally, we update the velocity. And then we can continue to the next time level. So here we have the SOLA source code, and it's not that big. You have some initial statements here, and then here we have the main time loop for time step to 0 all the way up to maximum time. A lot of calculations here. This is where you create the tentative velocity field. So here we find a new velocity u and a new velocity v based on just old values. So this is the first step, tentative velocity field. Then you have to address the boundary conditions. And that actually you have to do inside every iteration for this SOR algorithm, the successive over-relaxation algorithm. So here you will have the boundary conditions for all four sides. So the domain is very, very simple. You have x and y, and then you have a rectangle like this. It's actually a square. And for this code, I just choose the same number of cells in each direction. So delta x equals delta y. It's very, very simple, just to keep it simple. But here you have to specify the boundary conditions. And that you do inside these two for loops here and here. That's the boundary condition. Then here you will have a pressure iteration. You go one sweep of the entire domain, and there adjust the pressure and also adjust all the velocities. This one is then based on the SOR idea. What he also does, he calculates actually the divergence, as we spoke about, the divergence for one cell. du dx plus dv dy, and then you use the divergence to create an adjustment here, a delta p, which then you use not only for the pressure but also for the different velocities. Beta here, that's just a number which is calculated up here, involving the value omega. Value for omega is here interpolated, so depending on how many unknowns you have, he will provide you with a suitable value for omega. So you can choose as many unknowns as you like. Here I've set it to be 30 by 30 case. Then he will provide me with an omega 1.95, which is fairly optimal. After the pressure has done the iteration, or sort of the updating inside one iteration, you sort of investigate all the time if this divergence for the cells, if that one is bigger than a prescribed epsilon. If it's smaller, then you would say, okay, now I have found a solution. So you check the divergence for every cell, for every iteration here. And if all of them are small enough, then you say, I'm satisfied. Then I have a solution good enough. Or if you have done too many iterations, you're using the maximum number of iterations for one single time step, then you will be provided with a warning, and then he continues. So that is something that you have to pay attention to. Also here I just added a break in the case that he finds not a number, then he should stop the simulation. And that's it. Finally here, just a couple of graphical images. Velocity vectors, stream function, and the isobars. So let's try to run this one. So the default case, that is the test case called square cavity. The top wall is moving with a constant velocity, the three other walls standing still. So you have some fluid contained inside here, and due to viscosity you will be set up one huge vortex like this. Here Reynolds number is 100, and this actually is not a bad situation for a steady state. After here I think it's time 1 or something. The pressure, you will have a low pressure in this corner and a very high pressure in the other corner, of course. The velocity vectors look something like this.
What did you set as an acceptable divergence?
I have a parameter up here called epsi. Here you specify when are you satisfied, when the divergence for each cell should be smaller than a certain value. So 10 to the power of minus 6.
What is the reason for choosing that exact number?
You have to choose something. You can't say 0. So you can play around with bigger numbers, of course you can. Say epsilon equals 1. That's fairly big. I accept that one. Now, can you remember the solution here? Keep that one fixed in your mind, and then we run again. A little bit different. And also, one piece of warning here. You have a streamline entering a solid wall. Thank you very much. How's that possible? Of course it's wrong. So now something is wrong with the overall continuity here. It's not that bad, actually. Other questions? So let's undo this one. So when you start here, you specify actually only the Reynolds number, meaning the Navier-Stokes here has been written in a non-dimensional form. So I have chosen my velocity scale, u equals 1. My length here is 1. Also this one is 1. So a lot of things is given here, already sort of hard-coded into this logic, so you can't really do much about it. And the only parameter is then the Reynolds number, which then appears, as you know, before the viscous terms inside the Navier-Stokes. So we should be able to find them here somewhere. Here I update the velocities using first order Euler scheme here. And here I have the pressure gradient. And then I have a couple of terms here. Fux, Fuy, and some Vsu. And this Vsu, that's the viscous term, which is calculated here. And yes, it is divided by the Reynolds number. So that's the double derivative in both directions. Divided by the Reynolds number, and then also divided by the delta squared. So it's possible here to go through all the logic, how they have created all these different terms. Fux, for instance, that would now be this term here, u du dx, entering into the x component of the Navier-Stokes. And remember, for the x component of the Navier-Stokes, then it is this point we are focusing on. Creating this one, how would you do that? Well, you take, well, actually, you don't write it like this, you write it like this. ddx of u square. So you have to create a u square at this point. Then you use these two, average and then the square. And then you use these two, average and square, to find another one here. Then you take the difference divided by the delta. I think that's what they have done here. Yes. So yes, it's possible to go through all the logic here in the details. So I won't do that. You can do it yourself if you want. What we should look a little into is the boundary conditions here. What about the boundary conditions? How can we find these? Well, this is my domain, and I have, say, a very simple 4x4 cells, like this. These are my live cells. These are my internal cells. Here I have a solid walls around it. Or if I want to reprogram it, I can have an inlet or an outlet or something. That's okay. But my computational domain is this only. And now for the boundary conditions, I use ghost cells. So I have additional layer of cells outside the entire domain, like this. So here, additional cells. And inside these cells, I put my boundary conditions. For instance, the bottom wall, he should have a no-slip condition. And also, no velocity straight through the wall, of course. So down here, well, first of all, we need the numbers here. I have I and j. And sadly, in MATLAB, you can't use 0 as index. You have to start with 1. So there I have 1, 2, all the way up to n plus 2. I sort of add these two ghost cells. When I give the number n, I want to have n unknown inside my domain. So plus 2, that's for the ghost cells. So this one will now be n plus 1. Same goes in the j direction, 1, 2, all the way up to n plus 2. So let's look at the bottom wall. That has to be then for all the different i's. Start with I number 2, all the way up to this one, n plus 1. And I state down here, v I comma 1 equals 0. What was the rule? This is an arbitrary cell I j. Pressure in the center, Pij. The velocities, u to the right, v on the top, Ij. So here, this is an arbitrary I, comma 1. Then v is located at the top. So yes, the velocities here, they will be v number 1. Like that, in the y direction. And yes, they are set to be 0. So that's a solid wall. Same goes for the top wall. Then I have to use n plus 1. This is cell n plus 2. N plus 1 is this one. Here. Where is my v velocity located? At the top. Here. Yes, he's also 0. So this is also a solid wall. Then we have the u velocities. What about that one? The velocity here in the x direction, he's live. That's something we have to calculate from our numerical scheme. But down here, half a cell inside the wall, I have to specify something. I have to give him a boundary condition. And I have to do that so that I get a 0 velocity in between these two. Hence, I invent a negative velocity down here, if he is positive, so that in the middle between them, I get 0. Hence, u number 1 equals minus u number 2. Then I will have 0 in between them. For the top wall, that's a little more tricky. Here is a live velocity, and I have to specify something here. And I have to specify something here so that I can get a velocity of 1 in between them, no matter what he might be. Because this is my boundary condition at the top wall. And to achieve it, I have just added 2. That's all. So on average, between those two, you will find the value 1. The boundary conditions in the y direction, that will be this for loop, and they address in the same way. U is 0 here, no velocity through the wall, same on this side. And the v velocity, you have to specify something here. Then you say this guy, he equals minus whatever is inside here, so that you have 0 in between them. That is the logic for the boundary conditions. For this test case, a square cavity. Here you also specify how long time you are going to simulate, and you specify the time step, delta t. That is a trick. How big should he be? And if it's too small, it takes forever to simulate it. If it's too big, it explodes. And also here you can specify on each time level what's the maximum allowed amount of pressure iterations, of SOR iterations. Hopefully you should find a solution, but depending on how much CPU you want to waste, it's not certain that that number is big enough. If we look at the simulation that I run. He prints out for every time step the number of iterations that he has used. So in the first time step, he didn't need any pressure iterations. Of course, then the initial pressure, 0, was a good solution already. But when the wall starts to move and sort of pushes the fluid to motion, then he needs more adjustments. But you see, he doesn't need that many pressure iterations to obtain a solution. If we now squeeze him a little bit, say I increase my time step a little bit, try to run this one, then I get a warning. Delta T should be maximum 0.02. So he doesn't stop, he just gives you a warning. If you press a button, he will continue. And then he crashes. What's nice with this script is if you do something stupid, he crashes normally quite fast. So he did 2 time steps and then crash. So he's really, really sensitive. Okay, we better use a smaller delta T then. I crashed, but now it took some time before he crashed. If you look at the beginning now, he uses a couple of hundred pressure iterations on all levels. But now I have chosen a time step that is questionable. It's on the stability limit. So he has really problems finding a solution. He manages in the beginning here, but here he crashed. You get a warning, and the divergence is a little bit big here, quite big actually, and then he just aborts. If we go a little bit smaller, say 119, he crashed again. So the stability analysis here is not entirely correct, but we'll come back to that later. 18, I think it should work. Yeah. So now I am squeezing him a little bit. You see, I have a quite big time step close to the stability limit. He really needs a lot of pressure iterations on every time step to keep it correct. And I mean, this is something you have to do if you want to have the correct time development, if you're interested in how the fluid actually evolves according to the time in seconds. For this problem, he will actually settle and you will have a steady state solution. If you're interested in only the steady state solution, well, then you don't really care about solving the equations correct at every time step. Then I could say, instead of allowing him for using 300 iterations on every time level, I could say, no, sorry guy, you are only allowed to use maximum, say 10. Because I admit I can't find the solution on every time step. So now I will be satisfied if you just have sort of a solution, as long as you can continue in time. But then I must use a much smaller time step, or else it just explodes here. Let's try that one. No. Even smaller. Give him a 0. It's tricky. Okay, increase a little bit then. 30 pressure iterations. There he manages. So now I sort of have to admit I haven't solved the simulation correctly in time. But as long as I have simulated long enough, I should reach a steady state situation, which should be correct. If you look at the printout, I don't get enough printout, say from the beginning. Here, first time step works okay. Already the next one, he can't find the solution within 30 iterations. You have a divergence. It's not that big, but definitely not smaller than my prescribed epsilon. So you see he has problems for the first part of the simulation. He can't find the solution within 30 pressure iterations. But if we allow him to continue, there. Now he finds a solution within 30 time steps. Pressure iteration. So here I have a solution actually. And if I continue further in time, then in the end, nothing much should happen from one time step to the next. So the maximum time, say 20, should be okay, I think. Then I should sort of say, yes, I have a steady state, more or less. And at that time, you shouldn't need many pressure iterations, because remember, nothing should happen from one time step to the next. A little bit is going to happen either way, but not much. So here, maybe we should have continued even further to assure steady state. He's still using some pressure iterations for the different time steps here. So here you have the code. Play around with it. Try with different number of unknowns, different Reynolds numbers. If you go down with the Reynolds number, then what's going to happen? Reynolds number 1. That should be very sticky fluid, like honey or something like that. Then you don't need a big maximum time. But you're going to need a small delta t. Let's try it. Yeah, 0.000 something. Yeah, he crashes immediately here. So you are going to need a very small delta t. So here is Reynolds number 1. And you get a different solution. Reynolds number 1, the main vortex is going to be centered here. You have secondary vortices, one down here and also one down here. You actually have a third one as well with high Reynolds number up here. This code here, of course, doesn't have any turbulence model, so Reynolds number 10,000. Then we can have a bigger time step, I think. Let's see what happens. Ah, that was a little bit too big, I think. I'm not sure I believe that one. No turbulence model. So no, I would put some question marks on that one. Okay. Also, what you have been getting is an execute file. This one is actually a program I wrote in Fortran. So it is the same as the SOLA code. Let's just move him a little bit. Where are you? There we go. So let's play around with this one here, just for test. 30 by 30 cells. And the boundary conditions here, we have a moving wall, like that. And then we try to run it. overflow, we need a smaller time step. Yeah, I can imagine. So here you then should find the solution fairly quick. Now we can have some fun with it. Let's try that one. Then we can have a bigger one here, I think. Restart and run. Oh, that didn't help. Still a little too slow. There we go. Reynolds number 5000. It's pushing it close to turbulent, but he seems to be settled down without exploding. So we should sort of have the same image, one main vortex and then secondary vortices in the corners. So now we have a small vortex here, a rather big one down here, and also one third one up to the left there. So here roughly you should have the steady state. Things doesn't change too much now. A little bit unsteadiness. So here now you can plot stream function. You can have a look at the pressure. Low pressure here in the center of the vortex, and then high pressure top corner. You can put passive markers in and then see how they follow the flow. Not so easy to see that one, but never mind. And here, of course, if you go too high, Reynolds number 50,000, and restart, he will start getting problems. Again, it's not a turbulence model inside the code. It actually has a switch here using turbulence model, but it's not implemented. So if you try it, it's just going to explode. It actually seems to survive here. Yeah, this is something you can play around with yourself. Here it's a little easier than to change the setup. So for instance here, say you have a slip wall. It's actually without viscosity, like that. Then you say the outlet here, it's unknown. Then you use a Neumann condition, derivative equal to 0. And then we insert constant velocity here at the inlet. So now we have this situation. Now I want to go back to Reynolds number 1, and then I guess I have to use a very small time step. See if that one works. Yeah. So here, this one should be fairly straightforward. Constant velocity, and you have slip walls. So the streamlines are just going to be straight lines, no problem there. If we now say I want to have this part as a solid wall, now let's see what happens. So then I have a flow around a blunt object. But the Reynolds number is 1. So this is going to be sort of a symmetric solution, and it's going to be stable, as you see it is. If we freeze in this one, and then we raise our Reynolds number to, say, 1000 or something, we can increase the time step, I think. Reynolds number 1000, that's based on the length scale of 1. So maybe I need a little bit bigger. So the length scale for Reynolds number for the blunt body, that should be then something else. Let's increase it a little bit. Well, actually, we can increase this one a little bit as well. Like that. And then say 5000. Not 50, 5. Like that. So now he should start out with a symmetric solution, but then built into Mother Nature you will have this tendency for the alternating vortex shedding. So that should appear here. Let's see if he does it. Still symmetric. We can try to increase the time step. It takes too slow. It takes too long time. Yeah, now it starts. So this then is something built into Mother Nature. I didn't ask him to do this. So that's something he did by himself. Okay, any questions to this one? I will provide you with some exercises that you then can address using these codes. Then